So now we're going to do some example problems related to logarithms. So rewriting logarithmic equations. So write the logarithmic equation in exponential form, and it gives you a little example there. So we know this is log base 10. Why? Because they tell us. So we know it's going to be 10 to some power equals something. What's the power? Remember, a log is an exponent, so that means that this negative 3 is an exponent. Then this is your result. Is this true? Well, negative takes the reciprocal. 10 to the third is 1,000. So this checks out. They are indeed equal, right? I think all of them are going to be equal. We'll see here in just a sec. Same idea. Log base 5, so the base of the exponential is 5, equals the exponent, so 2/3, equals the cube root of 25. Now, 25 is 5 squared, is it not? Now, I know we've talked about this, but cube root is the same as raising to the 1/3 power. And when we have a power raised to a power, we multiply, so that's 5 to the 2/3. Okay? Property of exponents are going to figure big because we're dealing with exponents. Okay, rewrite this in logarithmic form. So what's the base of the exponential? 9. So it's going to be a log base 9, and it's going to equal, what is log? What is a log? A log equals an exponent, right? By the way, 9 to the 3 halves. Hey, that's the same as taking 9 cubed to the 1/2, isn't it? Just split that up. Now, I would argue that I could really do 9 to the 1/2 and then cube it. Would it make a difference? I mean, when I'm multiplying, it doesn't matter which order. The only reason I say that is because I know what 9 to the 1/2 is. That's a square root of 9, that's 3. 3 cubed is 3 times 3 times 3, so yeah, it works out to 27. I know they're not asking you to do that, but understanding how these gyrations work is going to be useful. Okay, what's the base of the exponential? N. So it's going to be log base n. What is the exponent? T. And then 10. Not necessary, but n has got to be greater than 0, doesn't it? Because it's the base of an exponential, and it's also the base of a logarithmic function, so it's definitely got to be greater than 0. Otherwise, this does not work. You can't have logs of base 0. You can't have logs that are of base that are negative bases. All right. Use property of logarithms. Solve for x. Okay. Ready? Steady. Log base 5 of 5 equals log base 5 of what? 5, right? To get these two to match, x would have to be 5, so x is 5. Now, if that bugs you, is there an actual process? Well, yeah, this is still algebraic in nature. This is all just algebra in another form. So remember how I said you could exponentiate? Well, what if I compose this with its, now as long as I do it to both sides, so what if I made this an exponent and this an exponent, right? So now I'm composing this with, why did I pick 5 like that? Oh, because that's a log base 5. So when I compose these, I get 5 equals x, because they cancel out, right? Now looking at this, there's two ways to go. Could you rewrite this in exponential form? Well, 3 is the base of the log. X must be the exponent. 3 to the negative 5th. Ooh, matching. X has got to be negative 5, right? Or you simply recognize that, hey, wait, log base 3 and 3 to some power. So log base 3 of something and 3 to some power, that's like f, and that's like f inverse. So I'm composing these and they're just canceling, so my answer is negative 5, right? That's it. Can exponents be negative? Of course they can. We're all good. All right, using properties of logarithms. There's no good way to do this. It would be helpful to recognize that maybe we have this function g of x equals 6 to the x. Maybe you see that. That's our outer function, 6 raised to some power. And then you see another function, which happens to be its inverse because we know that the log base 6, right, of x is the inverse of that. So what am I doing? Well, I'm running g, that's my outer function, and I got g inverse as my inner function. What am I doing g inverse to? 36x, right? Because that's the actual independent variable. So what's my final answer? 36x, because these cancel. That's it. All right, sketch the graphs. So here is, x and y. Sketch f of x, which is 5 to the x. 5 to the x exponential growth. y-intercept 1. How do I know it's 1 times 5 to the x? It's going to look like that, asymptotic to the x-axis. Now then, log base 5 is going to be the inverse, right? So that means that this point, which is 0, 1, becomes 1, 0, like we expect. And this ends up being the inverse, right, of that. Okay? So this would be g of x, and this would be f of x, just like that. Easy peasy. All right. Graph a logarithmic function. In this, find the domain, vertical asymptote, and x-intercept of the logarithmic function and sketch its graph by hand. How awful. All right, well, I'm going to actually sketch the graph by hand first, then figure everything else out, right? Okay. What does a log base 10 of x look like? Unmodified, a log base 10 looks like well, it looks a lot like, I hate to say it, this g of x here, right? It's hard to tell the difference when you're just doing the sketch. So in general, it's going to look like this, and the y-intercept, the basic y-intercept of just, if this is just log base 10 of x, that's what it would look like. So what has happened to this? This is where you get to use your function transformation knowledge. Well, I'm multiplying the log by a negative 10, and then I am doing something sneaky. I'm taking the log base 10 of just the x, right? But then what about that 2? Isn't that the same as saying plus 2? Right? Yes, it is. Yes, it is. All right, so what does this mean? Well, it means that we've got some work ahead of us. It means that this bad boy has been reflected. That's what this does. So this has been reflected over the x-axis. A little blast from the past. And it's been shifted up 2. Up 2, right? So it means that this graph has been shifted up 2. Now you wouldn't tell that, or actually it's been reflected, then shifted up 2. So what would that in general look like? Well, it would look like, so it's been reflected. So it's going to be, so it's still going to be asymptotic here. It's not the greatest graph in the world. It's going to go down like that, right? But it's been shifted up 2. Now it's been shifted up 2. That means that this is going to cross the axis somewhere different, right? It's going to kind of look like that, all right? Now, here's the issue. What is, well, first off, domain. What is the domain of this? Well, the domain for any logarithmic function is going to be from 0 to infinity, right? So we look at the possible x values, yes. We have to take logs of numbers that are from 0 and higher, right? So that would be the domain. If you look at the graph, that makes sense. What's the vertical asymptote? The vertical asymptote, it is x equals 0, which is a fancy way of saying the y-axis, right? And last but not least, the x-intercept. This is actually going to require a little bit of calculation, so let's so we're going to solve the equation 0 equals 2 minus log base 10 of x. Well, if you subtract 2 from both sides, I'm going to get rid of these negatives by dividing or multiplying by -1. Either way, it doesn't matter. Okay, what does x equal? We're going to rewrite that in exponential form. There's the base of the exponent, because that's the base of the log. That is the exponent. So what is the y-intercept? I'm sorry, x-intercept. 100 comma 0, so that's the x-intercept. There is no y-intercept because it's asymptotic to that, okay? So that last step is you set that whole thing equal to 0, and you just solve it, okay? Turns out you don't even need a calculator. So same idea here. Hopefully you recognize that we're taking a function, let's say that's f of x equals log base 10 of x, right? What are we doing to said function? Well, we seem to be adding 2, right? So we're taking f of x and we're adding 2, but we're also plugging in instead of x, x plus 1. So what's this transformation? Well, it's a leftward shift of 1 and an upward shift of 2. So we're going to take our log base 10, the same thing, right? We're going to shift it left 2 and up 2. So it's going to be kind of the same thing, right? 1, 2, so that's going to be a -1, and then up 2. So this point right here, what used to be, right, it's going to be at -1, +2. Now this used to be the intercept. Now looking at this intercept, we know that this is asymptotic about 1 back. So what is this asymptotic to? Well, 1 back from that would be -2, meaning the vertical asymptote is at x equals -2. What is the domain? Well, there's my limiting factor, right? It looks like I can go -2 and higher, right? Oh, you know what? I shifted that too far. Back that train up. I'm sorry, but I only shifted this 1 back and then 2 up. I shifted it 2 back. My bad. So what I need to do is actually take this and go like that. And so it's actually asymptotic, not to -2. That's not 0. That's 0, right? It's going to be asymptotic to -1. There we go. Which means that it's going to be -1 and higher. And if you think about this carefully, as you're sitting there being confused, how do you screw this up so badly? Well, -1 plus 1 is 0, so that's my limiting factor. And what is the intercept? Well, same idea. 0 equals 2 plus log base 10 of x plus 1. Okay, subtract 2. Don't panic. Rewrite it in exponential form. Base of 10, base of 10. Exponent, exponent. All right. What is 10 to the -2? It is not -20 or some foolishness like that. It is 1 over 10 squared. It is 1/100th or 0.0 as tenths hundredths, right? What is this? Well, you subtract 1. What is 0.01 minus 1? It is -0.99. That is what the x-intercept is. So the x-intercept is -0.99 times 0. Not too terrible, is it? All right. Describe the transformation of the graph of f that yields g. So what's the only change here? We've substituted for the independent variable x plus 7, so we have a leftward shift of 7. Done. What's the difference here and here? 2 things. 4. Now look, if you wrote plus 4 versus 4 plus, it'd be the same thing. So that's an upward shift of 4. And same idea here. This is a rightward shift 1. That's it. Okay, write in exponential form. So it's going to be, so ln is base e. So this is a log base e, so it's going to be e to the exponent equals e cubed. Wow, that's tough. But there it is. That's exponential form. This is going to be e to the 1/3, which is equal to the cube root of e. That's it. That's all I want you to do. By the way, did you know that, oh wait, you did know that raising to the 1/3 is the same as the cube root, right? All right, next, rewriting exponential. Write this in logarithmic form. Now, here's the fun part. This is an exponential. How do we get there? In other words, I want to write this so it's e to some power. Well, it's 1 over that, right? What does that tell me? It tells me it's negative. It's being raised to the 4th power. That means it's that, isn't it? So what is our base of our exponential? It's e, right? So it's natural log of something equals the exponent, which is -4. And then we're taking the natural log of 0.0183. That's in logarithmic form. What's the key thing? Recognizing that 1 over e to the something is the reciprocal. So if it was like 1 over 2 to the 7th, that's the same as 2 to the -7th. You're just going to have to get used to that, okay? Home stretch. Use properties of natural logarithms. Well, all right. ln e equals 0. So this is 7 times that. If I can figure out what the natural log of e to the 0th power is, what is e to the 0th? What is anything to the 0th? 1. What does the natural log of 1 equal? Well, that would be e to something equals 1. E to something equals 0. Another way to look at it, what happens to the natural log and e? They cancel. What are we left with? 0. What's 7 times 0? Lots of zeros. 0. Here, e to the x and natural log. What happens? They cancel. So we get 22. We're just composing something in its inverse. Ooh, tricky. Okay. Equals what? So you can make it into an equation if you'd like. Natural log is base e. So e to the exponent equals 1 over e to the fourth. Scratch, 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 scratch. I don't know. Wait, we're taking the reciprocal. That must be a negative exponent. And we're raising it to the fourth. And, oh wait. Check it out. What does this have to be? Question mark has got to be equal to -4, which means this whole mess is equal to -4. And those are some examples using the various properties of logs.